Hello friends, welcome to the polymeric materials in electronics next segment under the edges of polymer process engineering. Now here have a look at what topics we have covered previously. We discussed about the fluorocarbons. Apart from this, we discussed about the polyesters. We discussed about the polyxylylines, and all these subjects are covered under the definition types, different type of properties, synthesis and applications. So all these things we have covered in the previous segment. In this particular segment, we are going to cover about the polyvinyl, polystyrene, acrylic, polyamides, phenolics, persulfates, etc. All these play a very vital role in the synthesis of the polymers, as well as they are the polymers, and they are very widely used in the electronic application. So let us start with the polyvinyl. Now, polyvinyl, this refers to a group of polymers derived from the vinyl monomer, primarily vinyl chloride, and this is the structure, that is CH2 double bond CHCl. This double bond attracts the further polymerization process of this particular monomer, and they are widely used in different type of applications like in electronic industry due to their you can say the desirable properties, or due to their properties or inherent properties which can be widely used in the electronics application. And they are classified as vinyl polymers, and this can be further modified, or you can say the co-polymerized with other monomers to enhance the specific properties which is desired for different type of electronic applications. Now, through polymerization, these vinyl chloride monomer undergo a chemical reaction. These are known as the vinyl polymerization. This results the formation of a long chain repeating units, and they are linked together. So, you see here that this is the the polyvinyl or vinyl. Now, when we talk about the properties, because if we go for end use, then definitely we have to look into the different type of properties. So, first property that is in which attracts that is electrical insulation. They have the good electrical insulation properties, making them suitable for applications where electrical conductivity needs to be minimized. Then another property which is attracts, that is the thermal stability, and these polymers exhibit good thermal stability which allows them to withstand over a wide range of operating temperature, and sometimes you need a different type of a temperature or sometimes elevated temperature. So, obvious reason is that the things which are made of should not go on degradation. So, that is why if a large range of temperature will be there, then the things will not be get degraded. Then the chemical resistance. The polyvinyl shows the resistance to many chemicals like acid, alkali, solvent, and this makes them suitable for environment where the exposure to the various substances is expected. Then apart from this, the mechanical strength play a very vital role. So, this depends on the specific polyvinyl formulation and processing, and these polymer or polyvinyl can offer a good mechanical strength and durability. Versatility. This can be easily modified or co-polymerized with other monomers or functional groups to tailor-made their properties, and sometimes you may enhance the flexibility, impact resistance, or flame retardancy. Now, when we talk about their uses in electronics, the first and foremost use is the insulation. They are used as insulation material for wires, cables, electronic component to protect against the electrical conductivity and provide the electrical insulation. In encapsulation, the polyvinyls, they are used to encapsulate the various electronic devices circuit to provide protection against moisture, dust, and environment contaminants. So they create a barrier so that the exposure to these components with respect to the moisture, dust, and environment contaminants can be avoided. Then adhesive films. There are certain polyvinyl formulation. These can be used as adhesive film for bonding electronic component and substrates. Coating. These polyvinyl coatings, they are applied for the various electronic component and PCBs to provide the protection against corrosion. Cable sheathing. These polyvinyls, they are employed as a cable sheathing material to provide the mechanical protection and insulation for the cables used in electronic device and system. Flexible electronics, they are attracting more and more impetus nowadays. So the flexible polyvinyl formulation like polyvinyl chloride, they are used in the fabrication of flexible PCBs, wearable electronics and flexible displays. So they are the future polymers. Now let's talk about their classification. Now primary vinyls, they are formed from the polymerization of vinyl monomer, while secondary vinyls, they are formed by the subsequent reaction with the reagent that alter the polymer chain groups. Now polyvinyl acetate, PVA, this is an example of the primary vinyl which can undergo, because the presence of the double bond, which can undergo the hydrolysis to form the hydroxyl group, and that can react with aldehydes to yield the acetyl derivatives. Three important derivatives of polyvinyl acetate in the electronic industry, they are polyvinyl formyl, polyvinyl acetal and polyvinyl butyryl. Now, polyvinyl formals and polyvinyl acetal, they are commonly used as tough and high temperature resistant wire enamels. Acrylic polyethylenes and polypropylenes, they are also considered a part of the vinyl classification, although they are often discussed separately due to their significant commercial importance. So here you can see the free radical vinyl polymerization. So vinyl acetate gives you polyvinyl acetate. Here you see that another polyvinyl fluorine, polyvinyl carbazole and polyvinyl chloride, polyvinyl acetate, all these things are classified. Here you see the polystyrene, this is the classical formula of the polystyrene, the polymethyl methacrylate, they find their very wide range of application, polyethylene, polypropylene. Then this is the polyvinyl acetate, and if you see that hydrolyzed polyvinyl acetate, see the structure, this N represents the number of chains. Now here you see this is the polyvinyl alcohol PVA, and this which we are talking about, the polyvinyl formals and polyvinyl butyryl. So all these things you can see that the structural difference. Now polyvinyl formals, they find a various application in the electronic industry due to their desirable properties. Now we have enlisted some of the desired properties with respect to the electrical properties, like magnetic wire insulation. The polyvinyl formal coating, they are applied to magnet wires used in the transformers, motors and other electrical equipments, and they provide insulation and enhance the wire's dielectric strength. Then coil coating, they are utilized as a protective coating for electronic coils and transformers. Then electrical tapes, the polyvinyl formals, these can be employed in the production of electrical tapes for insulation purposes. Then film capacitors, they are utilized as a dielectric material in the film capacitors. Now dielectric strength and electrical properties, when they are in question, so let us talk about detail in about this dielectric strength. Now this polyvinyl formals exhibits high dielectric strength, typically ranging from 800 to 1000 volt per mil, and this property ensures their effectiveness as insulation material in the electrical application. Now when we talk about the dielectric constant of this polyvinyl formal is relatively low and usually around 3 to 4, which makes them suitable for application where low capacitance and minimal signal losses are desired. Insulation resistance, these are polyvinyl formals, they offer excellent insulation resistance, preventing leakage of electric current and ensuring the reliable performance in electronic devices. Dissipation factor, this factor of polyvinyl formal is generally low and indicating the minimal energy loss as heat during electrical operation. The temperature stability, they exhibit good thermal stability, maintaining their electrical properties over a wide temperature range. Now let's talk about the PVA or polyvinyl alcohol and acetates. The polyvinyl alcohol and acetates are not commonly used in electrical application. They have a high dielectric constant and dissipation factor. This makes them unsuitable for electrical purposes. Their electrical properties deteriorate rapidly and extensively in humid condition, and absorption of water under normal atmospheric condition makes the electrical measurement useless. And also they exhibit the poor thermal stability above 95 degrees Celsius in the presence of air. The PVA, they are occasionally used as a temporary coating for masking or as a acid indicator. They can be easily removed by dissolving in warm or hot water because they are having very close affinity with the water. And generally, these resins find greater use in non-electrical applications like paper coating, packaging films, and house paints. Let's talk about the polyvinyl chloride and fluorides, PVC and PVF. Now, PVCs, they are widely used as a wire and cable insulation material. It can be extruded from dry blend or hot fluxing. This PVC exhibits good electrical insulating properties, and you will find all these PVC cables in your domestic affairs where the metallic wire is coated with the PVC coating for the insulation purpose. So, this gives an idea that how versatile and how useful these polyvinyl chlorides are. And they offer the resistance to the moisture, chemicals, inherent flame retardancy. Now, the commercially available PVC, they have the molecular weight ranging from 50,000 to 1,50,000. Toughness, viscosity, and chemical resistance increases with high molecular weight. This we have already discussed in some of the chapters. And the average molecular weight determines the application and the property of the PVC resin. The high molecular weight PVC is used for wire insulation and flexible application or flexible tubing like water hosing, etc. You will find that all these are made of the PVC. While lower molecular weight PVC is used for the film production. Now, PVC is usually compounded with the plasticizers for flexibility because sometimes they stiff, and if you compare with the electrical insulators with the garden hose, then you will see that garden hoses, they are more flexible. That is because of the presence of the plasticizers. They are low molecular weight solvents, and when they embedded in a polymer matrix, they provide the flexibility. Now, they need some stabilizers to prevent the thermal decomposition because sometimes all these things may be exposed to the higher temperatures like electrical wires or garden hoses, etc. And also some lubricant and additives for processing and impact strength. Now, vinyl suspension coating are washed to remove the impurities when used as an electrical grade resin. Now, usually when we talk about the plasticizer, then the careful selection is needed because to minimize the degradation of electrical properties and moisture absorption. Because these are the low molecular weight solvents and because this provides the flexibility to the system. But simultaneously, there are wide range of solvents available as on date, but we need to look that if we are using for the garden hose, then the solvent or a plasticizer must be different as compared to the when we are using as an electrical insulation. Now, filler like clay or calcium carbonate, this can be added to reduce the cost and improve the electrical resistivity. There are large amount of fillers can negatively impact mechanical properties like abrasion resistance, tensile strength, elongation and flexibility. Now, stabilizers, they are used in the PVC formulation to prevent decomposition during the processing, cure or uses. Now, this decomposition occurs through the release of hydrogen chloride, which can ionize to hydrochloric acid due to the water present in the plastic. This HCl or hydrogen chloride can cause the corrosion or deterioration of the metal and other plastic in the electronic enclosure. So, it can also act as a catalyst for further polymer decomposition and releasing more and more hydrogen chloride. So, environmental issues are also play a very vital role. Now, acceleration of this particular process can occur at high temperature under the high humidity and the presence of certain metals like iron, zinc, maybe say around 150 to 160 degree Celsius. Now, these stabilizers react with and remove the trace amount of hydrogen chloride, preventing catalytic degradation of the polymer chain. Some of the examples of stabilizer includes lead, epoxide compounds, plasticized urea formaldehyde resins. Now let's talk about the polystyrene. Now these polystyrenes, they have found their wide application in such kind of utensils and other applications. So they are well suited for specialized electronic application and except for very high temperature requirement. So if you are having a moderate temperature requirement, you can use these polystyrenes, and they exhibit low dielectric constant and power factors similar to the polyethylenes, fluorocarbons and silicons, and they have high dielectric strength values comparable to mica and stable volume resistivity at high frequencies in the presence of moisture. Now, these electrical properties make them ideal for the capacitor, dielectrics and insulation at in high frequency circuit. Now, they are transparent, clear, capable of transmitting a large chunk of light and with a good refractive index properties, and they are used in coating lenses and other optical equipment due to their transparency. And they offer a very wide range of color for decorative purposes due to their excellent tinting and coloring properties. But simultaneously, they have some limitations like inherent flammability and a lower and upper temperature limit of say 85 degrees Celsius, which may not be suitable for various you can say the specific electronic applications. Let's talk about acrylics. Now, acrylics, they find application as a general purpose coating, impregnants for PCB protections, anti-corrosive coatings, wire enamels, and wire coil dope. And they are available as one component, low viscosity solution coating suitable for spray or dip application and can be air dried or baked. These acrylics can be used as a clear or pigmented protective coating and exhibit compatibility with various different type of surfaces. Now, excellent adhesion is achieved on glass, ceramics, epoxy laminates and other plastics and metals such as chrome plate, aluminum, magnesium, zinc and steel. Non-oxidizing alkyd primers can enhance the adhesion to metal. Now, acrylic enamel maintain their clarity and color characteristics at intermittent temperature, say up to 260 degrees Celsius. So, the maximum continuous operating temperature for electrical insulation, this can be ranges from 95 to 155 degrees Celsius depend upon the formulation. Sometimes fillers, sometimes stabilizers, all these may alter all these temperature range. Some electrical coating, they can function up to say 150 degrees Celsius, but their electrical parameter, they degrade rapidly above this particular temperature, and some sort of degradation may occur in situ. And the electrical properties of acrylics are generally good at room temperature, although they are not stable as those of epoxies or silicons across a wide temperature range. Now, let's talk about the alkalic polymers. Diallyl phthalate (DAP) is a monomer that can undergo alkalic polymerization to form the allylic polymers. Now, these allylic polymers, they are class of polymers that contains allyl group, that is CH2, CH, CH2 as a pendant or backbone unit. Now, they possess unique properties due to the presence of unsaturated allyl functionalities. Here you see that this is diallyl phthalate ortho position, and here you see that diallyl isophthalate in the meta position. Now, allylic polymers, they are commonly used monomers, and diallyl phthalate is widely used in allylic polymer synthesis and find application in electronic encapsulation, potting and printed circuit boards. Allyl methacrylates (AMA) This monomer combines the properties of allyl group and methacrylate functionality, and it is used in coating, adhesives, and dental materials. Allyl glycidal ethers age. It contains both allyl and epoxy functionalities, providing excellent adhesion and cross-linking capabilities, and it is used in coating, adhesive, and as a reactive diluent. Allyl acrylate AA. It combines allyl and acrylic functionalities, offering good adhesion and flexibility, and it finds application in coating, adhesive, and sealants. Allyl cyanate esters. It possesses both allyl and cyanate ester groups, providing high thermal stability and low dielectric properties. It is used in high temperature application like printed circuit board and microelectronics. Now let us talk about some related polymers and their uses like polydietyl phthalate, PDAP. This derived from DAP, which we discussed earlier, and it is used as an encapsulant and potting material for electronic components due to its excellent electrical insulation properties and thermal stability. Then polyallyl methacrylate, PAMA. This derived from AMA, and it is employed as a coating material for electronic devices, and they offer good adhesion and chemical resistance. Then polyallyl glycidal ether page. This derived from the age, and it is used as a matrix material in composite structure and as a binder for electronic packaging application. Then polyallyl acrylate, PAA. This is derived from the allyl acrylate, and it is used as a flexible coating material for electronic circuits, providing good adhesion and mechanical properties. Then polyallyl cyanate ester. This is again derived from allyl cyanate ester, and it is employed in high temperature electronic application like aerospace, defense, because of its excellent thermal stability and low dielectric constant. Let's talk about the polyamides. Now, polyamide resins, they have repeating amide group along the polymer chain, and they form through the condensation of di or polyamines with dibasic and or polybasic acid. Now, these polyamides can be classified into three main types: thermosetting fatty acid polyamides, thermoplastic fatty acid diamines, and nylons. Now, thermosetting polyamides, they derived from dimerized fatty acid and trifunctional amines, and they are widely used as a coating. Now, diethylene triamine reacts with the dimer acid, a mixture of dicarboxylic and polycarboxylic acid from linoleic acid, and this produces a series of liquid resins, and these resins can be used as a coating themselves or commonly co-reacted with epoxies. Now, the high concentration of amino groups in polyamide facilities the opening of epoxy ring and a cross-linking with multiple molecules. Now, epoxy polyamide coating, they exhibit enhanced adhesion and increased flexibility, improved surface wetting, and better corrosion and chemical resistance compared to the standalone epoxies or polyamides. Now, the polyamide resin, they can react with the phenolic and other resins. This results the highly cross-linked thermostatic coating. Now, thermoplast polyamides, they are formed by condensing dimerized fatty acid with a short chain diamine such as ethylene diamine. Now, these thermoplastic polyamides, they are soluble in many solvents and compatible with the different type of plasticizers and resins, and they can be formulated as solution coating, aqueous dispersants, or hot melt coating. So, both thermosetting and thermoplastic polyamides, they can be applied using spray, dip, or brush technique. And thermoplastic polyamides can also be applied using fluidized bed electrostatic spray or hot melt method. Nylon. Although the part of polyamide family, they have a different structure compared to other polyamides, and they are composed of a linear molecule formed by the condensation of aliphatic diamines with aliphatic dicarboxylic acid. There are certain properties attributed to the polyamides, like some polyamide resins, they have softening temperatures of say 110 to 200 degrees Celsius and hot melt temperature of say 190 to 250 degrees Celsius. And the coating derived from these resins have abrasion resistance better than polyethylene, but not as good as polyurethane and epoxy coating. The polyamide coating, formulated with the zinc, yellow or red lead or other pigments exhibit excellent corrosion inhibition properties. Now, extensive studies, some people they have carried out extensive studies on the corrosion inhibiting efficiency of the polyamide primers and epoxy polyamide coating with detailed data on the steel protection from salt water, because it's very important for the coastal areas, and then hydrochloric acid for industrial application, then hydrogen sulfide for various kind of the refining applications. Now, alkyd or oil based coating showed the least resistance to long term exposure to salt water. While polyvinyl chloride coating performed better, epoxy polyamide demonstrated the highest resistance. The polyamide coating, they are not widely used as an insulation in the electronic application or electrical equipment due to their marginal electrical properties, especially in the presence of moisture, and they have high water absorption compared to the other polymer types. Different ranges being studied so far for different type of a water absorbing capacity. Now, polyamide epoxy combinations, they are commonly used as a coating for electronic adhesive filling compound for the component vibration, damping and encapsulation. Now, let us talk about the phenolics. The phenolic resin, it was first developed by Bakerland in 1909, and they are the oldest completely synthetic polymers, and they are formulated and they are formed by the chemical reaction of phenol with aldehydes using an acid or base catalyst. The most commonly used resin is based on condensation of phenol and formaldehyde, and phenolic resin can exist in liquid or a solid form depending on their structure. The hardening and or curing, this is achieved by the heating of the resin alone, with either alone or with the hexamethylene tetramine, which acts as a catalyst and a source of methylene group. Now, this particular curing process, because this is a very essential process in any kind of a polymerization process, this curing process leads to the cross-linking of the resin molecules opposite to the hydroxyl group, and the phenolic varnishes, they are prepared from substituted phenols such as paraphenol or para-tertiary butyl derivatives by reacting them with tung linseed or other oils. Now, these varnishes can be air dried because atmospheric moisture plus air can react. So, this can be air dried. Baking is recommended usually for the optical chemicals and environmental resistance. Now, when we consider the properties, the major market for these phenolic resin, they are the molding compounds and laminates, and they are utilized for the electrical insulation, impregnating and the surface varnishes and the chemical resistant coating. These phenolic resins are available as a solution coating and can be applied through spraying, roller coating or dipping. So, after an initial air drying period to allow solvent evaporation, they are baked at temperature up to say 205 to 210 degrees Celsius for complete polymerization and optimal properties. Now, these phenolic coating possesses high thermal stability, excellent chemical resistance and good adhesion, and they are cost effective. Certain formulations, this can withstand continuous at a temperature of say 205 to 260 degrees Celsius with a minimum loss in mechanical or electrical properties. So, the mineral filters or mineral fillers, they are commonly added to enhance the high temperature performance and improve the electrical properties like arc resistance, dielectric strength and dissipation factors. Now, phenolic coatings, they are being replaced by epoxies in high reliability electronic application due to certain limitations, and they can cause the corrosion of metal like copper due to their acidic or alkaline nature of the catalyst used in curing process. Phenolic exhibits above average shrinkage, leading to the high stress, and moisture released during the cure can be trapped within the coating, degrading its electrical properties. Compared to epoxies, phenolic generally have the poorer electrical properties due to their highly polar nature. This results the high dielectric constant and dissipation factor. The high curing temperature sometimes required the phenolics make them unsuitable for the temperature sensitive electronic component, and some of these limitations these can be overcome by co-reacting phenolics with other resins, making them more suitable for electronic and electrical application. Let's talk about the polysulfides. Now the polysulfides, they are the organic polymers. This contains the sulfur linkage and mercaptan or thiol groups. The structure of polysulfide is represented by the presence of sulfur and mercaptans groups. Now, liquid polysulfides, the molecular weight ranging from 3000 to 4000 can be further polymerized to form the solid rubbery coating using oxidative free radical mechanism. Now, to achieve the polymerization, a second component or a curing agent need to be added to the polysulfide resin, and commonly used curing agent includes the dicumene, hydroperoxide, lead dioxide, manganese dioxide, calcium dioxide, zinc dioxide, all these are the peroxides. Now, polysulfide resins, they have the ability to co-cure with the various polymers, resulting in elastomeric and plastic properties based on the ratio of the ingredient used. Like epoxy resin, they combine with aliphatic or aromatic amines, and they are commonly co-cured with polysulfides. Let's talk about the properties. The polysulfide offer flexible and rubbery coating, and they are highly effective in sealing against water and moisture. And these coating demonstrate excellent adhesion to the various surfaces and are resistant to the solvent, oil, fuel, ozone, oxygen, etc. And their electrical properties are generally good. They are not exceptional. The polysulfide, they have the relatively high dielectric constant, typically around 7 or greater than 7. The electrical insulation resistance of polysulfide, this can decrease rapidly and irreversibly when exposed to humidity and applied voltage. The choice of curing agent can influence the electrical properties of polysulfide. Lead dioxide as a curing agent tends to yield better electrical properties compared to cumene hydroperoxide. The polysulfide, they find value in low cost electrical application like such as transformer coating, connector potting, sealing, and they are not commonly used for the circuit board protection or microelectronic insulation. So, applying a voltage potential across the polysulfide coated conductor pattern in humid condition leads to the decrease in insulation resistance values and decomposition of the polysulfide coating. The electrical properties of polysulfide can be modified by incorporating fillers. So, overall polysulfide exhibit poorer electrical and solvent resistance properties compared to epoxies. So, dear friends, in this particular segment we have discussed various polymeric materials they are used in the electrical electronics application, and for your convenience we have enlisted 4 references which you can utilize as per your requirements. Thank you very much.